Hi everyone, today I'll be presenting our recent work on heteroskedastic and imbalanced deep learning with adaptive regularization. This is a joint work with Yining, Junwei, Nichols, Adrian, and Chengyu. Heteroskedasticity is often studied in regression analysis and refers to the property that the distribution of the error varies across inputs. In this work, we mostly focus on classification, though the developed technique also applies to regression. Here, heteroskedasticity reflects how the uncertainty of y given x varies as a function of x. Real-world datasets are often heteroskedastic. For example, in healthcare, the quality of CTs varies among different machines. Low-cost machines unavoidably produce medical imaging with high noise. For object recognition, web crawl data contains a substantial amount of noise. Li shows that the web vision dataset has a varying number of ambiguous and true noisy examples across different classes. Over-parameterized deep learning models tend to overfit more to the noisy examples. To address this, a common approach is to detect noisy examples by selecting those with large training losses, and then remove or reweight them from the retraining process. However, an input's training loss can also be large if it is rare or ambiguous. Thus, previous methods could fail to distinguish mislabeled from rare or ambiguous examples. Though dropping the former is desirable, dropping the latter could lose important information. While previous works on simulated datasets often ignore this issue, it's very common in real-world datasets. Here we propose a regularization method that deals with all those uncertain examples in a unified way. Our key insight is that mislabeled, ambiguous, and rare examples all benefit from stronger regularization. We hypothesize that the weight of the regularization should be dependent on data density and data uncertainty. For simplicity, we consider a one-dimensional binary classification problem. The training objective is cross-entropy loss plus Lipschitz regularization. Here, ρx is a parameter as a function of noise level and density of x, and we derive the optimal choice by minimizing the MSE loss on the test set. The derived optimal weights should be proportional to the form given above. Intuitively, it means that examples with large uncertainty and lower density should have a larger regularization strength. For practical implementation, we divide the examples into k groups and estimate uncertainty and density for each group. Assume that we have a sufficiently accurate pre-trained model, we can use its validation error to estimate I. In order to simulate heteroskedasticity, we only cropped semantically similar classes. HAR shows improvement over uniform regularization with optimally tuned strength. We observed the behavior that too strong regularization impede the model from fitting informative examples, thus it could lead to a decrease on the clean class's accuracy. On the contrary, too weak regularization leads to overfitting to the noise examples, thus the accuracy on the noise classes do not reach the optimal. To understand the challenge imposed by the entanglements of heteroskedasticity and imbalance, and compare HAR with the aforementioned baselines, we further inject data imbalance into corrupted classes. Since examples from rare classes tend to have a large training and validation loss, regardless of whether the labels are correct or not, previous methods degenerate a lot in this extreme setting. Our proposed HAR is still able to achieve significant improvements. We demonstrate the trade-off between training accuracy and validation accuracy on mini-web vision with various uniform regularization strength. While a strong regularization could improve generalization, it reduces deep networks' capacity to feed the training data. For our method, we only enforce strong regularization on a subset so that we improve the generalization on the noisier groups while maintaining the overall training accuracy not affected. Thanks.